Hello everyone, this unit is Introduction to Complex Numbers or Complex Number System, and in this lesson we are going to study about the imaginary unit I. Whether you have heard about it before or not, I is an imaginary number or imaginary unit. As we have studied previously and we knew about, we always hear about real numbers. And this solution is or the domain all real numbers or this interval from real numbers. So by saying real numbers, it means that there is unreal number. So there is a parallel system of numbers, which is the complex system, other than the real number system. The complex system consists of imaginary numbers. So what is this complex system, and why we use imaginary numbers? Let's take this example here. Solve this equation: x squared plus 1 equals to 0. Subtract 1, we have x squared equals to minus 1. Now, take the square root. We usually say, no real solution. So we stop. X equals the square root of minus 1. So we stop here and say, no real solution. But from this lesson and on, we can't say that because we know that there is an imaginary solution for this equation, and it equals to plus or minus I, where I is the imaginary unit, and it is actually the square root of a -1. This is the unit. So if it is more than 1, -4, for example, -9, then it will be consist of real number and imaginary number, which is the complex system of numbers. This one here is the Cartesian plane. Our imaginary in the complex system Cartesian plane of the complex system, not real system. So as you can see, we have +1, -1 on, they lie on the horizontal axis of the Cartesian plane or the x-axis. So the real numbers lies on the x-axis, or we can say the horizontal axis, where the imaginary numbers plus I minus I lies on the vertical axis, which is y-axis, lie on the y-axis, which is the vertical axis. So the radical sign notation is reserved either for the real numbers, the principal square root function, which is valid for the positive numbers, or the complex system numbers. So trying to apply the calculations or calculation rules that are for real numbers, applying them on the imaginary numbers will result or produce false results for sure, because the rules calculations for the real numbers can't be applied or unapplicable for the imaginary numbers. I'm going to show you some examples for that. For example, we say that -1 equals 2, which is -1, which is I, multiplied with I. So it is the square root of -1 multiplied with the square root -1. So in real number calculations, the multiplication of a square root multiplied with a square root resulted to 1 square root, and multiplying this number with this number. So is this the square root of 1, which is 1? So -1 does not equal to -1. So this is a false result. That means the rules of calculations for the real numbers are unapplicable on the imaginary numbers or complex system. Similarly, if we take the reciprocal of I, which means the 1 over the square root of -1, and 1 is the square root of 1 actually. So is it okay to find it is the square root of 1 over -1, which is the square root of -1, which is I? Does I equals to the reciprocal of I? No, and this is a false result as well and incorrect. So the calculation rules for the real numbers are not applicable. Of real numbers, unapplicable on imaginary system. Complex or imaginary numbers. And these rules are, we applied here, these rules are when the square root of a multiplied with the square root of b equals to square root of ab, this is not applicable in imaginary world, as well as the square root of a over square root of b equals to square root of a over b as well, only in real number system. So don't do this mistake. For the square roots of the imaginary unit I as any non-zero complex number, it has two square roots. And the square roots are the positive or negative, the square root of 2 over 2 plus square root 2 over 2i. Okay, if we take a common factor here, it will be plus or minus the square root of 2 over 2i plus 1 or 1 plus I, the same. So to prove this, you can take the square root of it, the square root of negative, positive plus 2, square root of 2 over 2 plus the square root of 2 over 2i. Let's square this and we will get 1/2. This one here is 1/2 plus this one multiplied with this one multiplied with 2. The denominator will be eliminated, and square root of 2 multiplied of square root of 2 over 2 with I, it equals to I plus half I squared. If we take half out, then 1 plus 2i plus I squared. We'll be left with this one. I, as you know, I squared is equal to -1. So 1 plus 2i minus 1 multiplied with half. And 1 minus 1, this is 2i multiplied with half equals to I. So That's what we want to prove, that this is the square root of I. So the square roots of I are plus or minus the square root of 2 over 2 plus the square root of 2 over 2I. And I, it has a cubic root as well. So the cubic roots of I are the square root of 3 over 2 plus I over 2 and minus square root of 3 over 2 plus I over 2. In multiplication and division with I, so let's say we have a plus bi as a complex number. If we multiply this complex number with I, it will give us a I plus bi square. And if we substitute I square by minus 1, so it gives ai minus b. For dividing by the I, it's equivalent to dividing by or multiplying by the reciprocal of I. As we know, in real number systems of dividing by number, it's the same as multiplying by the reciprocal of this number. So 1 over I equals to, if I multiply it with, if I divide it by I, or the reciprocal 1 over I, so it resulted to 1 over I squared, which is minus 1. So we can use this identity to generalize division by I to all complex numbers. So a plus bi, it is a complex number. If we divide it by I, it always gives us the b minus ai. The powers of I, as you know that I squared, which is 1 to 1, and as I to the power 4n, which is an even number, equals to 1, I to the power 4n plus 1, which is odd number, gives us I, and I to the power 4n plus 2 equals to minus 1. I to the power 4n plus 3, odd number again, equals to minus 1, and so on. That's all about the imaginary unit I and the complex system. See you next lesson.